Namaskara. In this session, we will continue our discussions on the divide and conquer algorithm for inversion count problem. So, given an array A of n numbers, we assume that all of them are distinct and we assume that they are distinct, let us say integers. An inversion pair ij is defined like this: I is less than j, but ai is greater than aj. This is an inversion pair. We are interested in finding out how many inversion pairs. What we have seen is a divide and conquer algorithm in which if you want only given an array, it should output only the inversion count. In our divide and conquer algorithm, we have found inversion count for the first half, inversion count for the second half, and then we have to find cross count, and then we have to put all of them together to get the inversion count. The cross counting took in a naive way order n square, and then after sorting it became n log n. So, the combining cost is more, and the costlier step there is sorting, that n log n step. Suppose the recursive call returns a sorted sequence as well, right. Suppose it has returned the sorted sequence. I may not do anything with that, that is not even necessary for me, but suppose it has returned the sorted sequence. Then I can use it in getting the cross count in a much simpler fashion in linear time, because cross count is much like merging. Now I need the merged sequence also, because I want the sorted sequence as the output. Let us change the specification as follows. Given an array A, I need the following two outputs. The first output is inversion count. The second output is A dash 1 dot dot n, the sorted sequence. So, now you can see I am now demanding more. In addition to the desired output, I want A dash array, this is sorted version of A, sorted A array, the same thing, but it is sorted. I want that in a separate array, sorted. Now you see that we can design a divide and conquer algorithm that is more efficient. So, let us just go through the same divide and conquer algorithm. So, inversion count 1, this is a different algorithm, I see A 1 dot dot n, and it outputs IC and sorted version A dash 1. If again if n equal to 1, IC equal to 0, A dash n equal to A of n, same element, there is nothing to else. M is floor n by 2, and inverse count 1 applied on the first half, A 1 dot dot m, let it give IC 1. Okay. Let me change the IC 1 is used in a ugly way here. IC1 in the and let it give B the sorted version of this is B1 to M, B1 to M, and then inverse count A m plus 1 dot dot n IC2, you can call it as B or you can call it as even a C, another array, C output C m plus 1 to calling a new array with that index is a bit awkward. So, you can call it as a B, not a problem. B m plus 1 dot dot. So, you have two outputs, implementing in the first half you get two outputs, implementing in the second half you get IC1 and IC2 you have. Now, all I have to do is that cross count for B1 dot dot m, Bm plus 1 dot dot n, they are sorted. Okay. So, all I have to do is the following: cross count B 1 dot dot m, B m plus 1 dot dot n, let this give the cross count C C, and I need A dash as merged, A dash 1 dot dot n equal to merge of B 1 m and B m plus 1 n. Now, return then IC equal to IC1 plus IC2 plus CC. Now, you return IC and A dash 1 dot dot n. That is, now you can see this is T n by 2, this is T n by 2, cross count is order n, merge is order n, this is order 1. Anyway, now the recurrence equation is T of n is 2 times T of n by 2 plus order n, and that means this is order n log n. Order n log n. Now, you can see the improvement, because we have asked for more, okay, we have got an n log n algorithm. So, direct algorithm order n square, naive, okay, multi-pass algorithm, scan from J all the way to the left, and that is order n square. Divide and conquer algorithm, okay, direct, very simple and direct divide, and again is order n square. Divide and conquer algorithm with sorting done during the combining stage. During the combining stage, we are combining the solutions to get the final solution in the divide and conquer algorithm. There we have done sorting, and then we have done some more. There are a lot of things that we do. Okay. So, the divide and conquer algorithm I1, I2, solution 1, solution 2, then you do lot of combining of this solution, and so this is the combining stage to get the solution. Yes. This is our input, this is the solution for that input. When sorting done, then this is order n log square n algorithm. This is because the recurrence equation for this will be T of n is 2 times T of n by 2 plus order n log n. That is the reason why this is. Then divide and conquer with more for less idea. What did we want? We want IC and sorted version of input. This is not needed at all for you. You are given a permutation and you have to only get the inversion count, but I demand more. I change my specification to I want inversion and sorted. I may completely ignore and throw that product out. I may not use it at all. But when I change the specification like this problem can be solved in order n log n time, more for less. So, more for less is such a powerful idea, but what is important is to figure out what more if you demand you can gain efficiency. So, you look into the combining, the computations done in the combining stage, look into the hotspots, look into the most inefficient part of the computation done during the combining phase. For our case it is the sorting. There are 2 sorting that we did, and then we could very efficiently get the cross count. So, if you want to avoid that sorting, what we can perhaps do is we can ask the recursive routines to return the sorted sequence. If the recursion returns the sorted sequence, then I can use the output of the recursion, okay, and I can do the cross counting. If the recursion should return IC and the sorted sequence, my original problem must be rephrased to output the sorted sequence. So, let me write again here the contrast. I I1, I2, I have IC1, I have IC2. While combining, I have done the sorting and computed CC and then IC and then output IC. Instead, so this is when from the given input return the IC. So, for I1 you will get IC1, for I2 you get IC2. First half you get the IC1 in the. Now you are changing from the given input you get IC and sorted sequence from the given sorted input. Sorted, okay, I will write it. Now, splitting I into I1, I2. Now, I1 is going to give IC1 and sorted I1. This will give me, because this is the specification, recursive call gives IC2 and sorted I2. When you have sorted I1 and sorted I2, okay, here what do? I do the merge and I do cross count, both of them I can do it in, and then I get my output and sorted I. This process is order n. This process is order n. I have sorted I1, I have sorted I2. How do I get sorted I? Merge them. This is order n. Whereas this is here it is order n log n. Combining cost was, because I have changed the specification to this, I got these values which I can use during the combining stage, and I made the combining stage more efficient. I have reduced the combining cost. Therefore, I get a, this gives the recurrence equation T of n is 2 times T of n by 2 plus O n log n. This gives T of n is 2 times T of n by 2 plus O n. Therefore, this is O n log square n and this is O n log n. This is the power of the idea. Okay. We will see one more very interesting example of using more for less and that will be from computational geometry. We will take a completely different domain and then explore an interesting problem and then discuss the solution in computational geometry. Okay. I conclude this session at this point.